Hello everyone, in this video I'm going to talk about implicit differentiation using the chain rule. So suppose you have a function that looks like this. For functions like this one, it's going to be easy to find the derivative of y with respect to x. You simply differentiate the equation with respect to x, and you're going to get your answer, which says that dy dx equals 2x plus 2. The ddx over here are simply differential operators. It's just saying that we're going to be differentiating the terms with respect to x. And of course, dy dx equals y prime. They're just different notations representing derivative of y. So for functions like this one, it's not very complicated to find the derivative of y. But then what if now you have an equation that looks like this? Note that if you graph the x and y values that satisfy the equation above, then you're going to get a unit circle. So for some values of x, we have two y values, which means that according to the definition of a function, the equation at the top is not a function. We cannot say that y is a function of x. We can, however, say that y is implicitly a function of x. In other words, loosely speaking, although y is technically not a function of x, you can imagine y to be some function of x. And not only that, we can also figure out the derivative of y with respect to x. But in order to calculate derivatives when you're dealing with implicit functions, you should be using a technique called implicit differentiation. And so this is the main motivation behind using implicit differentiation. We use it when we want to deal with implicit functions. For example, like the equation of the unit circle that you see above. Now to explain in detail about implicit differentiation, I'm going to be using an equation that is different from this equation. And the reason is simply because I've already seen many people use the unit circle equation at the top to explain implicit differentiation. So I just simply want to offer you a different example. In particular, we're going to be using this equation at the top. And just like the unit circle that we just saw, for this equation, we also cannot say that y is a function of x. We can only say that y is implicitly a function of x. And that means that in order to calculate the derivative of y with respect to x, we need to use implicit differentiation. Now, if you're not sure if you're dealing with implicit functions or just a regular function, then just remember to use implicit differentiation whenever you cannot easily separate out the y from other variables in the equation. For example, if you cannot transform your equation into something that looks like this, where y is totally separated, then just remember to use implicit differentiation. And now to compute the derivative of the equation that you see at the top of the screen, I'm first going to show you the shortcut when doing implicit differentiation. And later on, I'm going to go step by step and explain all the concepts behind implicit differentiation. So when you're using the shortcut, the main thing you have to remember is that you're also going to be differentiating the terms with the y variables, just like you would normally differentiate the terms with the x variables. We're going to see soon that it's going to be slightly different, but we simply cannot ignore the terms with the y variables. And the reason we cannot ignore the terms with the y variables is because y is implicitly a function of x. So you can think of the equation above as the equation in the red. And this is why you cannot ignore the y's. So you're simply going to differentiate all the variables that you see in the equation. So that means the first term y squared in the equation is going to turn into 2y. And the trick here is that after you differentiate y, you're going to multiply that term, that differentiated term, with y prime. So you differentiate the terms with the y variables in the same exact way that you differentiate terms with the x variables, but you're simply going to multiply y prime after you differentiate the terms with the y variables. And for x squared, it just becomes 2x. That's it. Now for xy, we have to use the product rule. So then I'm first going to differentiate x and then leave y as it is. So then the first term here after using the product rule is going to be y, right? Because when I differentiate x, I just get 1. So then for the second term in the product rule, I'm going to leave x as it is and I'm going to differentiate y. So when I differentiate y, that's just going to become 1. But again, like I said, whenever you're working with the y, you want to stick y prime in there as well. So the second term becomes x times y prime. And also when you differentiate 1, you're simply going to get 0. So then this equation becomes 2y y prime plus 2x plus y plus xy prime equals 0. And here now, all you have to do is solve for y prime. So separate the y prime and send all the others into the other side of the equation. And when you do that, you're going to get y prime equals negative of y plus 2x divided by 2y plus x. So this is our answer. Y prime equals dy dx, which represents the derivative of y. Okay, so that was the shortcut. And now we're going to go over implicit differentiation step by step using the chain rule. I also use the chain rule in the shortcut process too. I just didn't explain about it. But now I'm going to explain everything, each step of the way. Okay, so again, we're going to work with the same equation that we just worked with. And for the first step, I'm going to apply the ddx operator to both sides of the equation. So I'm going to be differentiating both sides of the equation with respect to x. And so this equation is going to be the same as this equation here in the middle. So now I'm going to be differentiating each one of the terms in the equation with respect to x. Now here I'm going to define a variable f, which equals y squared. So f is going to be a function of y. And I'm also going to let g equals y. So what I'm trying to do here is I'm basically going to insert f into the equation for y squared and g into the equation for y. So the equation that you see here in the middle is going to become this equation at the bottom. And now I'm going to bring up this equation at the bottom to the top of the screen. So now let's take a look at the first term, which is d dx of f. And remember that f is a function of y, f equals y squared. So you might think that if we differentiate f with respect to x, we're going to get 0 because f is simply a function of y, not x. But you have to remember that y is an implicit function of x, which means that f is also an implicit function of x because f is a function of y. And this is why when you differentiate f with respect to x, the derivative is not going to be 0, so you can't simply just ignore it. But whatever the derivative is, I'm simply going to call it df dx for now. I'm just going to leave it at that, and we're going to calculate that later on. What about the second term in the equation, d dx of x squared? Well, that's easy. It's just going to be 2x. What about the third term, d dx of x times g? Well, if you remember, we let g equals y. And again, if we imagine that y is a function of x, we can also imagine g to be a function of x. So in order to differentiate x times g with respect to x, we have to use the product rule here. But whatever the answer is, I'm just going to call it d dx of xg for now. I'll start working on this term in the next step. Okay, what about the last term, d dx of 1? Well, that's simply going to equal to 0, right? So if we put all these terms together, we're going to get this equation here. Now let's focus on this term over here because I'm going to be applying the product rule to this term. So when you apply the product rule, one of the terms is going to be d dx of x times g. So I'm differentiating x first, and then I'm leaving g as it is. And the other term is going to be x times d dx of g. So here, I'm leaving x as it is, and I'm differentiating g with respect to x. And following the standard notation, I'm going to call derivative of g dg dx for now. We'll figure out what dg dx is later on in the video. Okay, then after adding these two terms, we get the following equation. Now note that d dx of x is simply going to be 1, right? If you differentiate x with respect to x, you're going to get 1. So this equation is now going to turn into this equation at the bottom. And the equation at the bottom, I'm going to bring it up to the top of the screen like this. Now I'm going to try to solve df dx and dg dx. Let's first focus on df dx. So if you remember, we let f equals y squared, right? So f is a function of y, and since we can imagine y to be a function of x, we can also imagine f to be a function of x. And so in order to get df dx, we have to use the chain rule that says df dx equals df dy times dy dx. If you're not used to this notation, you may have seen this other notation for the chain rule, which says that df dx is going to equal to f prime of y of x times y prime. But they're the same thing. I'm just using different notations. I'm simply using the chain rule here. Okay, so then the conclusion is that df dx equals df dy times dy dx. And it's going to be the same story for dg dx. If you remember, we let g equals y. So g is also going to be an implicit function of x. And that's going to mean that by the chain rule, dg dx equals dg dy times dy dx. So then now I'm simply going to plug in these terms into the equation over there at the top. And after doing that, I'm going to get the following equation over here. Now note that df dy is going to equal to 2y. And that's because if you remember, f equals y squared. So if we differentiate f with respect to y, we're going to end up with 2y. And so then for dg dy, we're going to get 1. Because g equals y, so if we differentiate g with respect to y, dg dy is simply going to equal to 1. Now since g equals y, I'm also going to plug in y for g in this equation. So after plugging in all these values, I'm finally going to get this equation over here at the bottom. And now I'm going to bring the equation at the bottom to the top of the screen. And all we have to do now is separate dy dx in the following manner. And then if I solve for dy dx, we're going to get our final solution that says dy dx equals negative of y plus 2x divided by 2y plus x. So then the conclusion to our problem is that for this equation, dy dx is going to equal to that term. And of course, that's also going to equal to y prime. And if you want, you can check that the solution here is going to match the solution that we got when we use the shortcut. So whenever I have to use implicit differentiation, I use the shortcut, of course. But I went through all the steps one by one today because I wanted to focus on the main intuition behind implicit differentiation and show you what's really going on under the hood. And finally, I did a little bit of extra work to show you the graph of our equation. And that looks like this. And in this region, y prime is going to be negative. And you can see that from the graph, right? The graph is sloping downwards. And also in this region, the region highlighted by the red color, you can check for yourself that y prime is going to be positive.